started looking at electron configurations, stating a little more certainly where we'd probably find electrons in terms of their distance from the nucleus. And we did several examples and worked on a worksheet to practice writing the electron configurations for various elements. Well, this tells us where an element or an electron might be. It doesn't really tell us what it's doing. In fact, we can be even more specific. I mentioned that there are very small areas within each sublevel called orbitals. Orbitals are areas that I would most likely find an electron, and it's a tiny little area big enough to hold exactly 2 electrons. Not only can we hold only 2 electrons in these tiny little areas, but they're going to have opposite spins. One of them is going to be spinning in a clockwise direction within that orbital, the other one counterclockwise. So let's take a minute to think about what an orbital is, and then why is it that they have to spin in opposite directions? Imagine for a minute that you had the world's most powerful camera, and you were taking a picture of the hydrogen atom. You'd see that you had a very small, very dense nucleus in the middle. And at the moment you took a picture and you saw the electron, it would appear as a dot somewhere within hydrogen's first energy level. But electrons, of course, move. So if you took another picture just a second later, you would get another dot. It might be close, it might be further away. Within the next second, we know that maybe that electron had jumped up to the second energy level. But in the third picture, it was back down closer to the nucleus. If we continue to layer our pictures over each other, and we label millions and millions and millions of these pictures over one another, we would start to get a picture that looked something like this. The picture that you would see would be roughly spherical. Now I'm drawing in 2 dimensions, but a sphere is like a ball. It would be in 3 dimensions. The area within the sphere where it was the most dense, where we had 95% of the electron most of the times, would be the orbital. And anytime we're measuring electrons in an S sublevel, the orbital is always spherical. When we take a picture and layer millions of pictures, we get the electrons in a shape that fills in very much like this. When we are looking at electrons in a P sublevel, we end up with a shape that looks like party balloons. P sublevels have 3 orbitals. Remember that the P sublevel can hold 6 electrons. So the first 2 electrons are in an area that looks like 2 party balloons tied end to end. Think about the party balloons that you have at a birthday party. Imagine tying 2 of them end to end. You'd have a shape like this. You'd have 2 electrons in that space. The next 2 electrons, we tie one to the other end now, would be on the y-axis. And then the third 2 electrons, you'd have one coming in and out from the page and one going in through the back of the page would be on the z-axis. So we'd have an x, y, and a z-axis. Now, this is a mess, and I can't imagine you trying to draw it. If someone looked over your shoulder at this picture right now, they'd be like, what is wrong with your teacher? There are great images of how the p orbitals might look in your textbook and online. We fortunately don't have to be artists. Chemists have ways of representing them. We represent an orbital simply as a square, or sometimes an underline. We're going to represent an electron as an arrow. It will either be pointing up or down. And quite often you'll see me draw little half arrows. It doesn't matter if you draw half arrows or full arrows. Each electron is going to be a little arrow. So my S sublevel, which we know can hold 2 electrons, would need 1 orbital. So I would draw 1 square, and I could put 2 electrons in it. My p orbitals, which have a total of 6 electrons, if I can put 2 electrons per orbital, I will need 3 orbitals. So I would draw a block of 3 squares. My D sublevels in the middle would need 10 electrons. If you forget this, you can always just count the squares in your transition metals and get to 10. If I can put 2 electrons per orbital, per square, I'm going to need 5 squares, 5 orbitals. So I'm going to draw a big long block and divide it into 5 squares. If I put 2 electrons in each square, I'd have 10. My F sublevel refers to the electrons that I find in the lanthanide and actinide series. There are 14 squares there for a total of 14 electrons. Therefore, I'm going to need 7 orbitals. So I need a really long set, and I divide that up into 7 sections. Now, why do they have to have opposite spins? Well, think about what we're talking about here. An orbital is a very, very small area of space. In this S suborbital, there are 2 electrons in there, and they both have a negative charge. Now, what could possibly compel 2 electrons, both with a negative charge, to want to be in such a small space? Well, a spinning electron acts like a magnet. So if I have 1 electron spinning in a clockwise direction, I will represent that as an up arrow. It would represent, for example, the north pole on a magnet. If I have the electron spinning in the opposite direction, counterclockwise, it might represent a south pole. Now, I've arbitrarily labeled these as north and south. It doesn't matter. When electrons have opposite spins, it gets them to have opposite magnetic character. So even though both electrons want to repel each other, because they're acting like opposite magnets, that allows them to be close enough together that we can fit them into this little small area of space. So how do I arrange my electrons inside those little squares? Well, there's 2 scientists here who did some work in it. Their names are Pauli and Hund. The Pauli exclusion principle says when I have to put 2 electrons, when I have to put 2 arrows into a square, 2 electrons into an orbital, they have to have opposite spins. So for example, when I consider just the valence electrons for the 3rd energy level, for sodium, magnesium, aluminum, etc. We know that in an electron configuration, that 1 electron for sodium in its outer shell is in the 3s1. An S sublevel has 1 orbital, and it has just 1 electron in it. We always start with an up arrow. That's just the general rule. We always start with an up arrow. If I need to put that 2nd electron in for magnesium, the next one must be a down arrow. So here's 3s2. Then we go into the 3p's. Aluminum's next electron, 3p1, starts as an up arrow. But we have a question. Should I put my next electron in the same square beside this arrow, or should I move it over 1? Hund says the answer. When we have electrons within a sublevel, so all these electrons that go into the p sublevel, he says spread them out first. Spread them out first. We put 1 electron in each orbital until they all have at least 1. Then we start to backfill. So we fill the electrons in, the first one up. Silicone has 3p2, phosphorus has 3p3. When we get to sulfur and we're at 3p4, we do all the ups and then we start backfilling with the downs. It makes sense if these are orbitals that are in different areas of space that it would be easier to spread them out first and then start backfilling. So let's try 1 or 2 of these together. I'm going to start by doing an electron configuration so we can refer to it. Let's try aluminum. I know the electron configuration for aluminum starts with 1s for 2, and then we'd have 2s2, 2p6, then we'd have 3s2, and then 3p1. My s sublevel is always one orbital. S's get one orbital. It doesn't matter if they're 1s or 2s or 3s. They get one orbital. I draw one square. P's always have 3. I know I need 3 orbitals, 3 squares, because these are groups of 6. So I'm going to draw a group of 3 squares. For this P, I'm going to draw a group of 3 squares. And now we're going to fill in the electrons. And I can see that in 1s there's 2 electrons, 1 up, 1 down. 2s has 2 electrons, 1 up, 1 down. For the 2p6, I need 6. Fill in all your ups first, and then backfill for your downs. 3s2, 1 up, 1 down, and 3p1. So get into the habit of doing all the ups first and then backfilling the downs, because it's important for us to recognize the direction of spin on the electrons. It has implications for later chemistry. So what I have up at the top is an electron configuration. What you see underneath with the squares is called an orbital diagram. Electron configurations are 1s2, 2s2, 2p6. Orbital diagrams show squares with the arrows in them. How would the electron configuration and the orbital diagram look for magnesium? Well, to fill in magnesium, we'd fill in 1s for 2, 2s for 2, 2p for 6, and then 3s for 2. That's my electron configuration. My orbital diagram is filling in the squares. I need 2 electrons in the 1s, 2 in the 2s, 6 in the 2p. Remember, all the ups, then all the downs. 3s has 2. By the way, we are also allowed to use the noble gas shorthand here. The last noble gas before magnesium was filling in all of these electrons. This matches up with neon. After neon, we added just the 1 orbital with 2 electrons. So this would be the shorthand version of an orbital diagram for magnesium. Let's try carbon. Carbon fills in as an electron configuration, 1s2, 2s2, 2p, 2. The orbital diagram with the electrons, we put 2 electrons, 2, and for the 2p, it is up and up. The last 2 electrons have parallel spin. There is lots of practice on electron configurations and orbital diagrams in your textbook in Chapter 5. Read Chapter 5.3 and do the following questions found on pages 160 to 168. In the back half of your workbook on quantum theory, the first 2 worksheets are just summaries of the electron configurations and the orbitals and the sublevels. Page 2 is a whole series of squares you can use for doing orbital diagrams if you don't want to draw them for yourself. But on pages 3, 4, and 5, there is a set of 10 questions to help you practice energy levels, sublevels, and orbitals. These questions are multiple choice format, so don't panic if it looks like a lot of work. It's not nearly as bad as it looks.